after the Ganesh Chaturthi or Vinayak Chauthi celebrations yesterday. And we are starting on a good note today after you relaxed for a day. So maybe you would have time to refresh some of the concepts that are there. So I'm also happy to inform you that we have completed all the basics of what do you say, computer, the requirements that are there for QT-01 course, that is linear algebra and probability statistics, electromagnetic theory, physics part, and then computer architecture and logic design. Everything is done. So we are all set to start the first course. Actual syllabus had QT-01. They did not have QT-00. So we are starting from QT-01 today. And we have with us Dr. C.V. Sridhar, who is from Tata Consultancy Services. He did his engineering from JNTU Hyderabad. At that point of time, it was combined Andhra Pradesh. And today, later, he did his executive postgraduate program in management from IIM Indore. And he has served TCS for a long period of time. And he's, as the TCS website says, he's head of research and and innovation. And it's a multiple roles that he plays. Strategic partnerships in TCS, and he's also actively associated with the Amaravati Quantum Valley Task Force with the government of Andhra Pradesh, and he has worked on various emerging technologies through Tata Consultancy Services, and he developed was one of the instrumental person developing 6-qubit quantum computer along with institutions like TIFR and DRDO, and of course National Quantum Mission, IIT Bombay, and others. So he's very much well known in National Quantum Mission and also the Amaravati Quantum Valley. And he is also the vice chair of Telecom Skill Development DSI, and he is an expert member of the Post Quantum Security Task Force in the National Quantum Mission. He's an expert committee on the Universal Service Obligation Fund and expert member on the syllabus for AICTE. That's another privilege that we have. The minor degree course from TCS side, he was one of the expert who created this curriculum. So we have one of the speakers today, and I will introduce you to more speakers who have actually been part of delivering this curriculum. We have Dr. Anindita Banerjee, who is taking sessions in the various courses at MNIT Jaipur. In QT-00, she's not speaking, but she'll be coming later. Dr. L. Venkat Subramaniam. So they were all part of the team which actually set up this minor course for AICTE. And who is best to introduce you the content and also quantum computing? So till now we did the basics. We will start with the first lecture, and that too we will have a broad overview on quantum computing. At the same time, because he is from TCS, the leading industry, a Make in India industry, what I can say, Tata Consultancy Services is an Indian company. But of course, having a global presence. So our own Indian quantum thought process, sir will share, and also the industry requirements. So of course, though sir will be leaving us a little early because of another scheduled meeting of the Department of Science and Technology. Without wasting much time, I will request Sridhar Garu to take forward. And he is our own person from Andhra Pradesh. So when I asked him, sir, can you spare time in the afternoon? He said anything for Andhra Pradesh. So let's welcome Sridhar Garu to take this session. Thank you, sir.
Thank you, sir. And some participants are in attendance as well. So thank you all for joining this session on the day after Vinayak Chauthi. And it's to hear that you've completed some of the basic sessions with respect to probability, mathematics, and some of the physics aspects. So I'm going to cover or introduce quantum related item. So it will be a very relaxing session, so you need not worry too much about the content. I'm sure you can sit back, relax, and listen to the content, understand more concepts that I'll be talking. And I've also shared some of the experiences that we have gone through. We've learned through this over a period of time. So I just a quick introduction. So as already spoke about me, but I come from a group called TCS Research, so which is a PhDs working on aspects of science and two parts to this one. The first team is working on research, so where the team is looking at what TCS should do beyond 10 years. And then there's a second team, innovation team, which is looking at technologies that are close to commercialization and how do we new technologies. Having privilege of working in this group, so I got exposure to working on some of this, and quantum is one such thing that we had started very early. So I'll take you through the presentation and slides, and in that one I cover the things that we were also doing there, and I'll keep it very generic, and because I have to share the presentation, so I have to remove some content, official content, and then I hope I'll be able to share as many slides as possible from this presentation. So we have about roughly about 40 slides and about 1.5 hours to complete this, and we'll maybe leave 10 minutes for question and answers. I'm sure you must be having a lot of but many of the things that today you will have to imagine because you have not seen the quantum machine in the real world. So, and this privilege starting on January 1st, right? The expectation is to bring IBM quantum machine to Amravati by 1st January, and once that is there, so you can all come down, see this machine, and then you feel it and all the things. But having said that, we have some wonderful professors and their labs in the country, across the country. So you can visit IIT Kanpur, Delhi, Bombay, Madras. You can see a lot of demonstrations of the technology in all aspects. So if you get an opportunity to visit any of these labs, feel these labs and these uh, technologies there. So with that, we'll jump into presentation. Just share my screen. So let me know when you can see the screen.
Yes, sir. You can make it full screen.
Sure. All right. Yeah. So all of you know, so of quantum science declared by United Nations. So we're about 100 years old into this technology, but a lot of developments have happened only in the last decade. A huge amount of progress, especially in terms of all aspects, I mean, computing, sensing materials, and all those things. A lot of action and traction from different stakeholders across the world. So quantum has produced approximately about 10 or 12 so far. Uh, so if you are setting a target for something working in this technology, maybe that's not a bad target to set, winning a Nobel Prize in quantum. And he aspires to be one of the top 5 hubs. And when we say we are the top 5 hubs, so we need to have this technology imbibed into our everything. So that can be one of the goals that we can start with. But and this is possible. We have to believe that it is possible, so we can do it. And if you look at last few Nobel Prizes that have come, so are actually centered around quantum. So I will come to that shortly. So in this session, I'll be covering some of these aspects. So we'll be talking very briefly about the why now inside a quantum machine. I'll just walk you through some of these aspects so that you get a feel of what goes into this machine and what such a machine and the complexity around it. And you'll also feel that it is multidisciplinary. We have implications for security, and I'll cover briefly about sensing and then some of the aspects of National Quantum Mission and the roadmaps that we are working towards. So this is I would request you can just sit back and relax and listen to this. No need any notes, so the content I'll share anyway. So it's very difficult to explain all the concepts of quantum so without showing some analogy. So the best way that we learned is to show an image of Hindu mythology of Hindu god with multiple hands, multiple heads, doing work simultaneously, right? So now we all have 2 hands and we are doing certain tasks with the hands that were given, and we coordinate them with brain and then try to do a series of activities. There are restrictions, some actions, but but assume you have multiple hands and you have full coordination and control from the brain. So you can generate significant power, and you can actually do a lot of multitasking and then able to complete uh, tasks in a way that you cannot imagine. And if you also coordinate, like putting couple of hands in one direction and two hands in other direction, and then you can do very, very interesting things. You can also do a lot of mathematical calculations. On our fingers only we do a lot of mathematical calculations. Now imagine if you have more fingers, more lines, you have ability to increase your computer, right? And that's exactly what is happening in quantum. So so it's a nice analogy. So this is the way we can imagine is the comes uh, in the Hindu mythology subject, where gods are showcasing the through the multiple simultaneous actions. So you can imagine, right? So sending multiple weapons through each of the hands and simultaneously coordinating shielding and everything. So all those things are possible. So think of a scenario like that, and that is what we're trying to replicate using quantum effects. Okay, so now let's uh, so so again, so we've been trying in a very, very simple term, very simple terms to all our customers without making uh, too much of science or technology into this one, because the concept itself is intriguing, and it'll be very difficult to imagine some of these concepts. Okay, so in the classical, I've always seen there are, it's like a switch. We have two bits, or we have something called classical bit, which is a switch, which is either 0 or 1. You can get that with a transistor. Like, so this is one of the inventions that, because of the development in silicon technologies and CMOS technologies and all those things, we are able to generate this zeros and ones very easily, and we started packaging all those things in a chip, and now millions of transistors are packaged into a small chip, which we are using it for computing. So in quantum world, so we use the principles of physics here. Mainly we use three concepts. Actually, there's also fourth component. We use three or four components which generate this quantum effects, and these are a little difficult to imagine, but let's say the first principle is called particle exists in state of 0 and 1. When you flip the coin is in air, so it's both head and tail till you measure it, right? So that is called superposition, and the state continues to be in superposition till you measure it. So we use that phenomenon. Power for calculations. And then we also have another very, very important feature called entanglement. So this is again a very, very interesting concept. Uh, yeah, one day a friend asked me, so how do you generate entanglement, right? So and so you take a photon and hit that with a crystal. It generates two entangled photons. There's special crystals when you hit them with uh, a photon using a parametric down conversion approach. You generate two photons. These photons exhibit a very, very special behavior. So irrespective of the same, right? And now you use this phenomenon to do a lot of things. So this phenomenon is called entanglement. So we use this, harness this, combine this with superposition, and do a lot of interesting things. Then we have math. So we have another concept called interference. So we must have studied this in our earlier part of science classes, like the sound wave interferences, etc. So the concept is the same. So which will help us to identify which are the crests, which are the troughs, and all those things where you know where the energy is high and where the energy is low. So which will naturally help us to do some tunneling. Again, so don't want to go into complexity now, but to simplify this, so these concepts, when you combine together and harness them, so gives opportunity when you convert this into quantum machine. Like when we first designed silicon, nobody knew that that can be converted into a processor, right? So we're now taking these principles and then converting this into a quantum machine. So which gives us the ability to do massive parallelism. You can naturally say of a solution of a problem statement. I'll come to a few examples to for your imagination. And then you can also achieve quadratic or exponential speedups. And in theory, the entire system will be energy efficient. Right now, they are not, because the way we generate all those things, we also spend good amount of energy those effects. But eventually, it will be very, very energy efficient. So the cost per compute, if you calculate, so it will be energy efficient. So now, you also imagine some scenarios of nature. These are the problems of nature, right? So like magnetism. So if you have a bunch of magnets and you put those magnets in a closed space, they automatically arrange to a of uh, stability, right? So, and it is naturally happening. And if I ask you to do the calculation and then do calculate how much amount of magnetic energy is there in that one, so we try to put complex equations to arrive at that one. Similarly, all our radio waves and all those things, we use complex Fourier transforms in our electronics classes to understand the movement of waves and all those things. Right? So again, in Fourier series, we talk about any wave can be represented in the form of sine and cos. So those calculations, now imagine you simulate them in nature and then naturally calculate. All right. So is that possible? Yeah, it is possible. So, or imagine another scenario like where you're dropping a ball from top of a hill and it actually bounces and reaches a stable state, and it is naturally happening due to the gravity, right? And so to identify what is that low ground state energy calculation, so typically we can write a bunch of equations and calculate, or apply these principles of nature and then try to calculate that minimum state. So quantum is something like this. Quantum is very close to nature. All the problems that are related to nature smoothly on this quantum machines. Okay, fine. So machine, so which can do these three things effectively, where you can do superposition, entanglement, interference. So you have the power. So you can do a lot of interesting aspects. So some of these aspects are simpler in simpler terms. We have represented the problem statements that you can work here. I will come to these things in detail, but at the same time, just want to share that uh, these are only a representative applications, and we may not know today what we can do in future with quantum. So we have about 156 qubits available from IBM today. So when we started this journey, we started with 7 qubits. So with 7 qubits, we were thinking of solving big problems, and you can imagine the size of the problem that we can solve is extremely small, and nobody will like it. People will say it's a toy problem you're solving, right? But we have to believe that yeah, you will get millions of qubits down the line, and once you have millions of qubits, how do you work on those things? So we have many problems that we can solve in quantum using quantum, and um, many of these problem statements uh, offer enormous transformative value. This report of BCG says we can create. They have actually put billions and trillion dollars of worth value that quantum can create. So there are plenty of applications. So in simple terms, you can only think that any optimization problem can be better solved with quantum. Uh, any AI ML problem can be accelerated. So all simulation scenarios can be accelerated. So these are some of the things that you can do. And any problem that reflects nature can be better solved on using nature itself. Like for example, if you're solving problems of molecular simulations, quantum computers are best compared to the classical computers. And now it has become very common that people are using hybrid approaches with classical plus quantum together to solve these kind of problems, and world is moving towards that zone. So these are some of the applications that we're working on. Okay, so now when we said okay, these are machines that are available, and how are these machines looking like, and who are making these? So these are some of the examples of companies who are working. From TCS side, we are talking to each one of them and then trying to understand their roadmaps, what they're doing and what is coming out from them, and how do we access these machines, and how do we submit our problem statements onto these machines and run and find the solutions, right? So these are some of the machines. So here there are two concepts. The first one, a universal quantum computer, which is a full-blown quantum computer like our classical machine, where you can do any task on it. The second concept is called annealer, so which is like a partial quantum machine. So it uses only certain principles of quantum, and then this is effective to solve optimization problems, right? So we have companies like D-Wave, Fujitsu. They are creating annealers. So we also have Fujitsu, which is also creating digital annealer. So there are also companies that have put open source annealers that are available on GitHub. You can take that code and then compile it, and then you can actually solve optimization problems on that one. And we have also semi-quantum machines, which are called, say, Ising machines. So these are not fully quantum, though it solves a particular equation. So it's called an Ising machine. So these are all some of these quantum kind of machines that are available, right? The universal quantum computers are coming from IBM, Google, Rigetti, IonQ, Xanadu, Atom Computing, and Quantinuum. And these are some of the companies that are making quantum machines today. We'll go into a little bit more details. Uh, yeah, but the thing is here, so the universal quantum computer is like a dream computer where you can solve anything on this one, whereas an annealer is suitable only for solving a certain kind of statements, especially optimization. Right. So the machines look something like this. So we'll also do a teardown analysis or a breakdown of one of these machines, how it look like, what these parts are, and all those things in the coming slides. Right. I talked about the speeds. So what are these quantum computers they achieve? So you can achieve either a quadratic speed up or an exponential. Like for example, if you're doing a million operations to solve a problem, which is 10 power 6, you can solve the same problem in 1,000 steps in on a quantum machine. So that is the speed up that is expected. So the other class of problems is a problem that takes 2 power t times can be solved on t times in a quantum. Either get one of these two or somewhere in between two, or do a hybridization, you get less than the actual number of operations that you do on classical machine. So that's speed ups that you get. And and is it suitable for any? It is not. So it is only suitable for problems that are complex, probabilistic in nature, and things like that. So what we typically say, if you say ask a quantum machine what is 2 plus 3, so probably it'll say it is probably 5 and it is not exactly 5, right? So so the small problems, we do not want to waste energy by for using energy by using quantum machine. So we only send a complex problem onto this machine and then try to solve that problem. So now imagine, so some of you must be working on AI and machine learning problems. You have, when you use deep neural networks, you take a network like UNet, so which has got, and we will not be able to solve the full UNet network on this machine. But what we can definitely do is we can partially send that problem, convert that network into a quantum problem and send on to this machine, and we can solve that problem, right? And so that gives us a little bit of quantum advantage. So what it means is, so you take a full problem statement, identify which parts classical machine, which part you need to push it on quantum, and then how you run those parts on quantum. So that decision making itself is again science and art. So you need a different set of skills to do those things. So naturally the question comes to what kind of problems I'll work on. Again, see some of those problem statements in the coming slides. Uh, yeah, but the thing is, so not all problems are good for quantum. So you only have to choose a right problem statement to put that on a quantum machine, run those problems on quantum machines. All popular players today are working on this one. So you name in Microsoft, Google, AWS, Rigetti, IonQ, and so many hardware players are coming. So Honeywell is one of the oldest players. They are merged with Cambridge. Uh, other high-based players are coming. is it difficult to make these machines? So these are very expensive today, requires a lot of cryogenics and other technologies that goes behind these machines. But to understand a little bit more, so I think you need to understand what is the physical implementation of these things. Right? So these machines are built with some underlying technology, right? And the most common is superconducting. So the superconducting phenomenon can be generated with cryogenics and semiconductors. So when you reduce put the certain kind of semiconductors to absolute zero temperatures, it loses all the resistance, and then there's superconductance, and that superconductance is harnessed to build this quantum machine. And all our MRI machines will operate on the same principle. Right? So we tap the superconductivity and phenomenon to generate the qubits, and these qubits we use for solving the quantum problems. So we talked about those principles of superposition, entanglement, and interference. So they can be different methods, and scientists around the world have been proving. Is a question? If you have a question, so you can stop. Sure. So,
Participants, please do not raise questions which are not related. The lecture is going on. Quiz questions need not be asked. I am really surprised why you are doing like this. You should listen to the lecture when the lecture is going on. No queries on quiz will be answered. As of now, some of the participants are writing their second attempt of the quiz one because they scored less than 4 marks. And because of that, you are not able to see the quiz marks. Is it the thing that you should be worried when such an important lecture is going on? I am surprised. We are all faculty members, and sir has taken his important time to be with us. So I will stop the chat now, right? If there are important questions related to the lecture, then sir can stop and answer your questions. I think please try to understand what is important.
sure, sir.
So,
Yeah,
sorry,
thanks.
sir.
No, no problem, sir. Actually, yeah, if you have any questions related to, please feel free to interrupt. That's okay. Uh, I'm not aware, so that you can take offline. Okay. Implementation. So you have different methods in which these quantum effects can be generated. So scientists around the world, so they've been trying to harness these technologies using different methods and build these qubits. Okay. So these are some of the common methods that I had listed here. So the superconducting is very common. The one that we are going to get in Amravati is based on superconducting quantum computers. So trapped ions, we have companies like Honeywell, Quanti, IonQ. So these are companies that are using trapped ion methods to generate qubits. Photonics, so we have a company called Xanadu, which uses light-based approaches for generating qubits. Then annealing, we have used there's a company called D-Wave. I'm not sure exactly what they use underlying technology, but it's annealer. So we also have a digital annealer, which is coming from Fujitsu, which is completely FPGA and semiconductor based, solves up to 53 qubits. Then we have quantum dots. So this is one of the newest technologies. So it also got Nobel Prize in 2022. And then we have the topological qubits. So this is what Microsoft is advocating, Mariano processor. So it's a kind of, again, semiconductor only. Uh, but they say its path to scaling is significantly high with topological qubits. So these might be new methods. In fact, I have heard from one of our scientists from a chemistry lab. So they've created chemistry qubits. So it's interesting. So I've not seen many papers around it, but the scientists explained with a lot of passion how these qubits can be created with chemical methods. So also there are means which means I want to leave a message here that the new methods are also possible, right? So while these are some of the common things that we know, there might be new methods with which you can create these qubits as well. So right now, so all these significant amount of investments into these technologies. So we can say Europe uh, has a long history because some of the scientists are coming from the European region from long time, and they're also good with optics. So they're a lot of optical related companies are uh, coming from the European region. Uh, around advantages. So there are each of these methods are good in certain way. They have their own advantages and disadvantages. So, for example, we are tracking two technologies. One is superconducting, then the other one is neutral atom, which is not in this list. So each superconducting has got its own advantages, easy to generate, scalable, and now uh, we've got IBM that is generating about 156 qubits. Similarly, there's another technology called neutral atom, so which is again based on optical tweezers. You create atoms and then control those atoms to certain set of arrays. So they generate qubits which are of good quality. Right? So all the qubits are more stable compared to the superconducting qubits. So each of these methods have got their own advantage, uh, and some of them are very scalable. And there are also other principles called coherence, or the decoherence, about the stability of the qubit, how much time you can hold those qubits, information in that qubits, and all those things are important. So, so the each of these underlying technologies, uh, but they're suitable for certain specific actions. And so, depending upon the problem statements, you will have to make it. But that gives more questions to us, right? So typically now I'm saying we have different technologies, and all these technologies are based on different physical principles. And who will understand, learn so many technologies, and then write software for each of these things, right? So there's a initiative going on. So to abstract this entire hardware. So just like in today's classical computer, we don't worry too much about underlying transistors or the hardware part of it, right? So we use a operating system like Linux or Windows, so which will completely abstract this. And then we have upper layers where we go and work on the applications. So it's exactly the same way. Here we have something called Open Chasm, so which is an alliance which is coming and putting a system software layer, you can assume, which will abstract this entire thing. So code that you write on Qiskit technically should work in any of the quantum computers in future. Right now it is not possible. Uh, so again, we've experimented different kinds of technologies and their underlying software specific software that is provided by the hardware. So let's say we're working with, say, an organization called Pascal, so which is a neutral atom based computer. So we use their software. We also work with Qiskit. We also work with Alien. Uh, are they interoperable? Not very much. Yeah, they are interoperable, but not uh, very much. And technology is evolving there also. So in future, so you can assume there will be a universal language where you can write these quantum programs and push it onto any of these machines, and the results you'll be able to get the results. But the underlying technologies have also got physical measurement and physical outcomes which are different. So we'll wait and watch how these things will evolve, how these things will get standardized. So Open Chasm is one such alliance that is looking into all these aspects and standardizing this entire quantum hardware. Sure, you don't worry about buying any type of the machine, so it should work universally and then give results in the same way. Okay, so this is an example of quantum machine. So looks something like this. It's a superconducting hardware. So we'll come to this some of the parts here shortly. But the one that we are going to get in Amravati is something similar to this one. So we'll have one enclosure like this, and this holds about 156 qubits. So now you can imagine 156 qubits. So there's a processor at the bottom here, and this is a cryogenic dilution ref. As you go from top to down, the temperature decreases. So you have to maintain this temperature gradients, also controls qubits and make the measurements through which you have to read. And this entire thing is controlled by a setup like this, which is the control electronics. So these control electronics will control these qubits and then help us to make the calculations. So to maintain these temperatures, again, we use helium gas So the helium gas is pumped into this one to get these temperatures. The temperatures will go to as low as 10 millikelvin, at which the superconducting effect is seen. So people always why do we need these low temperatures? Can we get the superconductivity at different different problem statement? So there was one paper last year about generating superconductivity at room temperature, but that was considered to be a fake paper by Koreans. It was rejected. So that itself is not possible. So in future, if somebody gets some materials which can generate superconductivity at room temperatures, we don't need this kind of setups. Our setups will look completely different. But for now, so this is the which we generate superconductivity, and we need to design a system like this, and then control electronics, and then this operates like a computer. And today this costs as much as $100 million each machine. Uh, so a lot of parts that are there, complex engineering it is, and then and India scientists started experimenting. I'll just come to that one about the parts, etc. Shortly, but again, not to deviate much from the story. These are the state of the art technologies, and these are the numbers that are available from these labs today. IBM with 156 is the state of the art. So they're getting a new processor, uh, which is very well connected. Say qubits, so the qubits are also connected internally. So now you can imagine qubit as an atom which is connected to every other atom that is out there. When all those atoms are connected, so you see the molecule which is behaving exactly the same properties, right? So we have to imagine a system like this. So IBM, you can also connections between few of those qubits, it's okay, but you can handle that in software. So most of the people attempt higher number of qubits with limited connectivity also, or the depth of connectivity. So you can generate qubits like that and play with it, because it's a complex engineering challenge to connect all the qubits with each other, and as this network grows it becomes more difficult, right? And that is where the and IBM has achieved this up to 156 qubit. So Google is working on 105. It's mostly operates on a stealth mode. We don't know what's happening. We don't get much news from Google. Occasionally we get info about their processors. AWS has recently launched their, and they've also shared their news. Similarly, we have Rigetti, which has got an Indian. So this is another machine. So they were at 81 qubits, 79 of their versions. Then we have IonQ, which internally uses something, they calculate something called algorithmic qubits. So this is another interesting technology in which they generate. Then we have Pascal, which is a neutral atom-based computer, and then we have D-Wave. Pascal has got about, so their roadmap is about 200 computers. So we were able to access maybe around 30 is what experimentation. And D-Wave is another one, which is an annealer, which has got about 5,000 qubits. But these 5,000 are annealer qubits. These numbers very seriously now. So which also raises one more question. So how do you benchmark which one is powerful, which one is good, right? So that questions come. So this is again a topic that is evolving. So there are papers that are coming up from different players. IBM has given their paper on how do you measure this quantum volume. So the term that is used is called quantum. So it's you have number of qubits, and these qubits are connected to each other uh, with certain depth. So what kind of problem you can solve? So one simple way is you take a common problem and run across all the machines and find out how much time it is taking, right? But that is not just sufficient. So what people have done is they come up with frameworks to benchmark these machines. So still the topic is evolving because the quality of qubits is not uniform machines. The connectivity is not uniform, so the power of these machines is not uniform. Uh, just in benchmarking these things. So so that that also has another challenge. Like for example, if I'm starting to solve a problem and I have to put it on, say, let's say Rigetti computer. So how do I calculate how many qubits are required, right? So that's another problem statement. So it's called resource estimation. So for example, we encountered a scenario where we want to do a image inferencing, right? So again, we took the same unit layers, and then uh, train the model using classical approach, and then try to quantum approaches. So there, so when we try to estimate the resources, the cost it is coming to is each image is taking significantly higher amount of dollars to do an inference of one image, right? So, and that is not economical. So today the scenario is like that. So IBM for some info. So what they say is the cost of each qubit is $10,000 today, and unless it becomes $100, this will not appear commercially viable. And we are on the path towards that. As we get more number of qubits, so the cost will reduce drastically, and then so there are also a lot of engineering efforts that are going on in terms of open sourcing a lot of this hardware. So like for example, all these parts are given to many startups to build those parts. So the costs, when a lot of players are working on it, the costs will come down, right? So the good amount of efforts are going on in terms of reducing the cost of these machines today. So if you look at the pricing, you can just go to Amazon or AWS, or sorry, you can see the pricing of some of these machines, because you can access these machines from AWS and Azure portals. So the costs are as high as $48 per minute for Amazon, so for IBM machine. So that's how it's right. And the problem that we run on this machine is only for a shorter amount of time. So we don't run for longer times also. Uh, so and you have many problems that we solve. So let's say, so I have some examples here what you can do with the number of qubits. But let's say Markowitz model, which is a Nobel Prize winning for portfolio optimization, and this is a 1952 Nobel Prize, right? And that is used in most of the risk scenarios. A variant of it is generally used by many companies uh, in insurance and portfolio asset management. So to do this 40 asset portfolio, so the matrix, because you'll not be able to run it on a classical computer. And if you increase this number of assets, the problem scales exponentially, and you'll not be able to solve this. You can solve with approximately 40 qubits. So that's the beauty. Uh, really, so there are many problems like the caffeine molecule simulation that IBM talks about can be solved in 100 qubits, right? And we have mul- multiple small molecule drugs, or the medium-sized molecule drugs can be solved with about 1,000 qubits. So today we suffer from a lot of noise. So these qubits are very noisy. So while the physical qubits are 156, so we may not get the real power of 156 qubits because of the noise with this machine. And so we in the real world we get less number of qubits accessible to us, and that actually creates a problem. So now error correction, uh, but even in future, so we'll have better, good quality quantum computers, so which will help utilize the full power of quantum and solve these problem statements. Right. So these are problems people are working on. So some of the investment banks are working on this Markowitz model or a variant of this model, because most of these banks have got their own version of the portfolio optimization mathematical models. Similarly, so people are working on problems related to chemistry, material. So all these things you can consider them as problems of chemistry only, right? So people are trying to work on the problem statements related to this, and and there are again problem statements related to drug industry, so which are pharmaceuticals. So today almost every pharma company all big pharma companies are working on quantum. So there is something called QFarm, so which is from a group called Pistoia Alliance. So there 17 pharma companies have come together and started learning together on quantum. And the best part is like all of them are learning and all of them are very new. So timing is so right that we're entering into a technology at a state where it is nascent for many of them, and we're trying to do massive transformation through these programs like FDP, where large section of people are trying to learn and apply these technologies. And more importantly, we'll get access to a quantum machine that is available for us, which is not possible for many countries. right? So, but we will have this machine available, and for AP, we'll also have, IBM is also providing about, I think, 365 hours of costs, which will be available to all the researchers, so they can use this and try these problem statements on that machine. So getting access to this machine itself is a significant advantage, and you can now imagine and try running problems of significant size on these machines. So why is it important? So last few years, so if we trace it back to last 5 years, so good amount of activities happening on this one. So the number of patents are increasing on this, and the amount of funding that is happening on startup side is significant. Some of these companies are already listed on New York Stock Exchange. So there's a lot of activity from venture capital, and billions of dollars of funds are flowing into this industry. And then we have three Nobel Prize uh, prizes in chemistry awarded in 2023. Actually, in 2024 also it was physics. Nobel Prize was for quantum, and actually no 2024 the Nobel Prize for chemistry has gone to the drug discovery use cases. So mainly for the protein folding. So it's about a 50 years of research that they've created protein folding, which is AI problem now. So two scientists, one of them from Google, the other one from University of Washington. So there were two Nobel Prizes. It was shared Nobel Prize, and both of them related to protein prediction, protein structure prediction. So these are problems that are very nice for quantum, and you can actually take those problems and run. uh, So which means we will have an opportunity to take their research protein structures and then create new drugs easily. Programs are mostly related to generics, means we have taken patented drugs and then bulk manufacturing of those drugs. But if you look at COVID, we have something called mRNA, which Moderna has used, which is a mathematical way of solving the COVID vaccine problem. So we can now do such kind of things. So once you understand the protein structures, you can play with it, affinity reactions, and then you can solve those problems for new diseases. So now you can imagine taking such problems and then solving those problems on quantum machines, and that is the expectation on us. The amount of investments is also significant. So the multiple national missions going on across the world. So India runs National Quantum Mission, and then we have many hardware players are coming. Then we have about 30 countries who are having national quantum as a national program, right? And this, as per this BCG report says, we can create about $50 billion of value in the next 15 to 20, and this number keeps increasing. Actually, we've seen a lot of changes in this number. So McKinsey has recently published a report. Again, they have also used significantly higher number on the advantages of quantum computing. So when there's a lot of noise, when a lot of people are investing, countries are investing, governments are investing, a lot of actions, and these patents are actually coming from big companies like Honeywell, Samsung, Microsoft, and others. And then this action at Nobel Prizes, and all those things is pointing to a significant transformative technology that is shaping up through quantum. So it's time that we also invest into this technology and then harness this and take our innovation to next level. So we've been working on classical computers. We're good at software, uh, but also gives us an opportunity next level, and where we can make this engineering capabilities of making the quantum computer itself and then harness these quantum machines on the sides of classical compute, get enormous power. And it is not sufficient if you wait and watch, because we've already seen what happens when there is a war like scenario, right? So nobody will support us, and then we'll have to have our own technology. So we have seen restrictions around semiconductors. We've seen a lot of export controls across all strategic technologies. So it's our responsibility to invest early, get into this tech, understand all the nitty-gritties. Nobody is perfect. Nobody knows everything here. Most of them are experimenting throughout the world, and then we also are going through the same process learning this step by step and then getting more powerful. These are some of the initiatives that are going across the world. So Europe runs a flagship program. It's called European Flagship Program, and they're doing a lot of work around computers and communications. There are also regional specific alliances. The alliance in Germany called QTAC, which brings together all the top 8 German companies, and they're experimenting quantum. They have clusters which are working on quantum technologies. They are very good with optical technologies. If you look at all the camera companies, they're coming from Germany. They're good with photonics. Uh, so we're also good with applying these things to sensing. So, example, many of these optical sensors are actually coming from companies in Germany. Right. So, a lot of action in UK is doing a good amount of investments. So first they created, I think 1.3 billion pounds program, and then they enhanced it by another 2.5 billion. So total it is about 4.3 billion pounds program. So they started in 2013. So UKRI is spearheading, and they have similar strategy like our Indian National Quantum Mission kind of model. So they also have clusters which are building these technologies. So India, we have this mission mode program which is going on. So we are working on 4 themes on computing, communications, and security, materials, and sensing. So these are the 4 areas in which we are working. US, again, US is doing a lot of activities based on the CHIPS Act. They have notified this as one of the again, they're working on multiple fronts. They have best of the labs that exist. The research labs are very active, also doing a lot of activity around security. Then we have Australia, Japan. They are also working on. So these are other countries that are actively working. Canada is another one. So all these countries are working on uh, quantum technology, and most of them have got a strategic program defined around this one, and and making significant for the building the capabilities from all directions. We'll just jump into a little bit deep dive into this machine. So this is an example superconducting based quantum machine. So looks like this. Maybe it's a little bit older version of the machine. So looks little clumsy with all the wiring, but the new one from IBM is very sleek. It's got a okay. So this is another example of the 6-qubit quantum machine that our professor Vijay Raghavan from TFR has made. So this, you can see the image here with a small processor. This is 6-qubit quantum machine, and this goes into the dilution refrigerator here. So you can also see the helium gas tank, so which is used for generating the electronics is there inside this box. So today we have very few companies that. So this refrigerator, I think based on this color, maybe you can say this is from Oxford Instruments. So the companies that are making these parts. So these are some of the parts that goes inside this quantum machine. So first there is a quantum processor, a processor like this, which is a kind of semiconductor, uh, so which exhibits superconductivity effects at very low uh, low speeds, sorry, low temperatures. And then you have a bunch of components that are there. So first you need a dilution refrigerator, which is this amplifiers that help us to transfer the signal whenever there is a change of temperature. You have flex wiring. You have a lot of coaxial cables that goes in. Then you have cryofilters and attenuators, because a lot of these wires behave differently at different temperatures. So now you're talking about absolute zero with superconductivity effect. So your work. So you have to have the wiring that works in. And then we have microwave enclosures. Then there's a magnet, then a processor. So these are all different parts that goes into making of a quantum machine. So again, go back here, so you can see the qubit signal amplifier. So it's breakdown. Actually, IBM, maybe probably IBM will give us some more information about. They have got some nice uh, uh, videos and collaterals that are available. So probably which we will get to Amravati and deploy once we put that. So they have showed us in a nicely all the parts that goes into it. So in Japan, so they have asked the local ecosystem to make this uh, make the parts of these parts by the local players. So they are open to they are willing to open source this entire design. So and they're expecting entrepreneurs to come forward and build these components. So you have cryogenic insulators, quantum amplifiers, mixing chambers, this cryo shield, superconducting coaxial cables, microwave lines, and signal amplifiers. So these are all the wires, amplifiers, and the processor itself, and the cryogenics around this one. And so, and IBM is actually open to share this design and asking people to build this products, and they're willing to purchase. Right. So that's how the market is shaping up. So this is an example of an Indian system. So we also have a startup that is coming up, a startup that has built. Most of you must have seen the news about QPA working with AP government. So this is their version of the system, so which is exactly the same. So the entire thing is put in this enclosure, and we have control electronics, the helium gas chamber, and the temperature chamber here. Right. So the making these machines. So once you have the know-how, may not be difficult. These parts would require the skills of precision engineering, making these components work in the expected way at ultra low temperature. So those are the things that we're looking at, right? So uh, and more importantly, so all this control electronics is actually nothing but signal generators and controllers, GA boards, so which is uh, deep-rooted electronics knowledge. So which means to make this machine, so we multidisciplinary skills of mechanical engineering, the cryogenics, the materials, semiconductors, electronics, and finally we abstract this entire thing with a software layer and then write algorithms on top of this machine. And I connect to this machine using cloud and then transfer my programs onto this controller, which then to this quantum machine, and then we get the output. This output is nothing but measurement here, which is the result. Right? So, and this is we imagine this quantum machine. Now, imagine these things getting very, very compact and also getting centers. So, right now we are putting these things go into on buildings. Let's just like our old style 1975 computers. Right. So these things will become smaller and smaller. There are claims from China that they made desktop versions also machines, but we are not sure. So, but there are also other technology scale, like say the photonic quantum machine, which might have um, more qubits and lesser can occupy lesser space. So those are some of the things possible, right? So today, buying this machine is very expensive and it is not easily possible. So yeah, so what we do typically is we create an equivalent simulator, so which most of these companies provide simulators, and we install the same simulator on our laptop and try to experiment on those simulators. So on our classical computers, we can go up to, depending upon the processor and memory, we can go up to certain number of qubits. So we've gone up to 27, 28 for certain problems. I've also seen a machine coming from a French company, which can go up to 46 qubits. They claim 46. I don't know whether I've not tried, tested. Uh, People have reported 33, 34 kind of qubits. Beyond that, it's breaking on high-end GPUs based machines. So NVIDIA also advocates a strategy. They say that while you get access to this full-blown quantum computer with millions of dollars, so why don't you try it on our existing NVIDIA GPU system, which can simulate about 40 qubits, and you can try all your programs up to 40 qubits on my machine, and then move your application to a real quantum machine. And actually, that's a good approach because you have to define the software engineering lifecycle like that only. So because you cannot experiment on this machine every time, and it is expensive to access this machine. So you take a big problem, now reduce the size to a small problem, and then run it on simulators of small size, and then again take the problem and put it on the real quantum machine for a few minutes. Right. So that's the way we follow. That is the software engineering life cycle, typically followed by a quantum engineer. And we are hoping that these machines of high performance computing, and then they stay together. So problem statement, like if you are using a, so already people are talking about AI based drug discovery methods, right? So now you're saying quantum plus AI based drug discovery, where you transfer the part of the problem statement onto quantum machine and get the results in an accelerated way, and then gain advantage of speed and time. So that's what so we're trying to do. So yeah, our goal is to build these kind of machines. So we should set our objectives for building all these components and these machines. That we will be one of the world-class hubs. So the goal is to also make these components locally. So, and we have to understand from the experts like Vijay Raghavanji, and then uh, try to manufacture these components for India, and then try to build a quantum machine. So that's the expectation, and we are building all this foundational knowledge for this one. And the startup has done it. So they're a 25 qubit. They're also assembling a 64 qubit machine. Today you can assemble this. So you get all these different parts from different vendors. So get a processor from a company called Quantware. You get dilution refrigerator from a company called Blue Force, and you get the control electronics from a company like Zurich Instruments, and then you get helium gas from one of the nuclear stations, and then combine all these things, and then should be able to build this. You get amplifiers, wires, and all those things from different vendors in Japan, Korea, and Germany. So technically, you'll be able to assemble this machine. Anybody should be able to assemble this machine. And when we are young, when I was young, so we were building our own classical assembly of our classical machines also. So now it may not appear a great skill, but quantum we can definitely assemble. So so the goal, I think the message for all of you is to understand these components. So and then see if you can designs are available to you. So let's say the design is given by IBM to you. So will you be interested to take this? You can do a startup and then try to manufacture these components. Right. So now let's shift a little bit to the software. We have another 20 minutes, 25 minutes. So I'll take you some of the problems and explain. So these are not new. You must have read this. I want to explain in a convincing way. So what is an exponential problem and why you need a quantum machine, right? So this is a map of a uh, uh, problem called traveling salesman problem, which is taught in optimization every time. So we have different solutions. So I can put a constraint saying that I should not come back to the same city, or I can come back to the same city. So then your equation changes. It's n minus 1 factorial by 2. And then when you try to solve this problem, so you have the numbers here for your imagination, right? So if you have 5 cities, it is only 24 routes which you can solve with pen and paper. But if I make this 10 cities, I'm just doubling the number here. So you have 312,000 possible routes, 12K uh, possible routes, and you have to calculate each one of the route and then find, right? Now I'm increasing to one city, so it goes to 3.5 million possible routes. So it has actually gone up by 10 times, so more than 10 times. And then now if I jump by another city to 12 cities, it goes to 39 million routes, right? So imagine 300K versus 3.5 million versus 39 million, right? So the problem is actually exponential. And if you go to 20, so you don't want even to count this number, right? So many routes you need to calculate. So all these things, the problem is scaling exponentially. There are many problems. So where the problem scales exponentially, but you have to solve this in linear amount of time, right? So I will, even if you increase the city, I will only take linear amount of increase in time. So that is possible with quantum machine. So this is a very good problem uh, that can be solved with quantum machine, and you can linear amount of time. And otherwise, you can also solve by applying matrices and all those things. So looking at every path and then solving this as a transportation problem, which is given to us in our operations management. Uh, so we study optimization techniques. So there, this was modeled as a matrix, and then you reduce that matrix continuously to solve this problem, right? So with quantum, you can solve this problem in a polynomial amount of time instead of solving this on exponential amount of time. So this is one good example. Similarly, I talked about caffeine molecule. So this you can imagine about the computation aspect here. So to simulate this molecule like this, so it requires 10 power 48 bits is what is required to simulate this molecule. But what we have today is about 10 power 16. So maybe this number is a little bit 1 year old. So let's assume 10 power 18 bits. This is the total amount of power, compute power that is available if you put all the computers together. And what we need to solve this problem is about 160 qubits. So if you have a very good quality noise-free qubits, you can simulate the same problem in 160 qubits. So we talk comparing between the entire world power of classical compute versus quantum machine, right? So now what we are talking about is 156 qubits that is available at Amravati. So which means you are very close to solving this kind of problem, and soon we'll have 1,000 qubit machines and a million qubit machines available. So these are easy problems for us, for our chemistry teams to handle these things. Sorry. So now imagine, so this is the kind of power that we are getting. So we're trying to solve uh, uh, simulations or small molecule or large molecule problems, which with qubits, and then reach a significant amount of simulation capabilities, which will help us to reduce the time for solving this drug discovery kind of problem. So we'll typically takes 10 years to bring a drug. So now we are trying to reduce 2 years by accelerating the compute. Right? Even today, so our scientists are working on technologies without quantum computer also. So they started shifting their approach towards quantum inspired approaches. So quantum inspired means they're thinking in the terms of modeling this problem like quantum on a classical machine and running it on HPC processor and getting value out of it. So we published some papers around that one, and these are very well received by the community. And so a huge advantage of even doing like that in the short term. So which brings to another point, saying that by working in quantum technologies, our existing skills in classical technologies will also improve, right? So I can tell my own personal case. So I was working on image processing problems and time series forecasting problems. My knowledge has actually improved working on quantum, because now I have to understand the classical, and then only I'll be able to benchmark on quantum. So I did that, and then also did on quantum, and then try to do quantum benchmarks, and then try to compare them and improvise the performance. So you will have that advantage. So all the efforts that we are putting on classical will only enhance when you start working on quantum, and you'll be able to do better comparisons and better visualization of things. How do you improvise the compute capabilities? Right. So another example. So it's another complex problem. Just putting it for reference. So this is something that we were aspiring to do, but we could not. So this is a multi-energy distribution source. So we have something called energy internet platform. So where multiple sources of energy are transmitting power onto the grid, and we create a grid with solar and solar panels and biogas plants and other things. And we also have power coming from the electricity network, and all of them. And these are now added with now battery energy storage systems. So it has become a complex network now to maintain the grid stability, right? And then you should also give an option for customer to define consuming power at the lowest cost, right? So when you model this, it becomes a complex optimization problem. So which is very difficult to solve, and this has also got a time constraint. So in many cases, you will not have time constraints, which means you can take some unlimited amount of time to solve the problem, and if you get the result, that is fine. But many cases like this, you also have time constraint where you have to solve in the next 5 minutes, right? So this is a very good case for a quantum problem. So companies in Europe, the utility companies in Europe are attempting this problem on quantum technologies, right? So these are some of the examples. The other examples can be the problems related to workforce planning, or the airport crew scheduling, then capacity utilization, or take the problem of an Amazon. So where you have multiple variables and multiple constraints, right? So you are trying to deliver manager has to make a decision on what kind of truck he has to use, what should be the size of the packet, which route to follow, and what time he has to deliver the and all those are decision points. And if you try to solve this problem, you'll not be able to solve that, right? So in general, what we are doing is we are taking one by one, step by step. We fix the network first, then we fix the truck, we fix the size of the packet, and then try to calculate the time of the route, and then put apply constraint on the customer delivery time, and then try to solve this problem step by step. But with quantum, so you will have this opportunity to do these calculations multiple times, uh, because quantum gives the ability to solve the problem with the multiple constraints. So these are some of the examples that are possible. So these are some of the TCS examples. A lot of use cases in this one. Uh, so when we started our team, so we started, what we did was we got a couple of experts from who are from the quantum background, and we have transformed our AI and machine team into quantum. There was a lot of resistance initially because uh, those days quantum is not a fancy technology, and nobody was very keen to join the team. But a few people who came onto the team started working on these problem statements. So these are some of the examples that we've solved. Some of them for them are our own problem statements for TCS products. Some of them are problem statements given by our research groups, different variety of problems, and some of them are given by customers. And this problem, one problem here, which is given by BMW, which is a BMW quantum challenge problem. Okay, the problem here, yeah. So absolutely, artificial intelligence can be used on all these problems. So most of these problems are either category of optimization or machine learning or deep learning. So here this is a deep learning use case. So now I want to bring one analogy here. Like for example, if you are working on image processing kind of use cases, all of you must have. If I ask you to identify a crack on, say, let's say your TV screen, right? So human eye has got inherent capability to the crack. You can directly point to the crack and say there is a crack here, right? And um, and but if you're trying to solve this problem on uh, or using machine learning approaches, your mathematical approaches, what you do is you take the TV screen, break each one into small pixels or small parts, right? So let's say you have a screen of 43-inch. So now you break that screen into small size blocks, and now you start analyzing each block, compare that with some information whether there is a crack or not, and then you try to identify and arrive at that part where exactly that crack is, right? So first is identifying crack, and then localization of crack on the screen itself is a mathematical problem. That is what we are trying to do artificial intelligence. So that's the reason why artificial intelligence consumes a lot of energy, whereas our brain, which is very powerful, so we are naturally quantum. So the moment you look at this, you'll be able to say that there is a crack, right, in your eyes, and once you experienced it, you know that it is a crack, it is a crack, that's it. So the the amount of energy that is spent to identify that crack is significantly less as human, but a machine will take a good amount of time, right? So now with quantum, applying quantum technologies, we are trying to solve these problems, bringing this better accuracies, better speeds, and with low historic information, means you need good amount of training data in classical world, but with lesser number of training data, you can actually solve this problem efficiently than the classical approach. So those are some of the things you can imagine can be solved, right? So these are all examples. So maybe at some point we will ask a TCS resource person to walk once you build some familiarity with these use cases. Uh, but again, to classify, so three category of use cases that we are working on. So first one is optimization. Second one is machine learning and AI/ML. The third one is simulation. So these are risk simulations or financial simulations, financial modeling, etc. Things like that. Right. I also have one cybersecurity use case that we're working with customers. So this is more of protection of the cases. The protection means, so suppose this quantum machine is available with bad actors. So they use the same power to break the encryption keys. So we have to protect ourselves. So the technologies that we used, so we We took support from AWS. We worked on IBM Qiskit. We also worked with Microsoft Azure. We worked with D-Wave, IonQ. So these are, again, many more technologies are there that are not listed here. So we worked with all of them and then try to solve these problem statements. And today, you will not be able to show return on investment of this outcomes. And often people ask questions, right? So is there a return on investment if I try to invest in quantum right now? So right now it is not there, but it will come. So in chemistry and these kind of problems, we are seeing already seeing some advantage. So you will see it. So right now, because the quantum number of qubits are limited, so we scaled down the problem significantly and then solve them on quantum machines and then take out the outputs. But in future, we'll have higher number of qubits that we 10,000 qubits, sorry, $10,000 per qubit to $100 per qubit. So we are in that transition. So when it becomes $100 per qubit, so this commercially viable and it makes economic sense. And that's when everybody will start using them. And we are in that transition cycle. And that is the reason why we have to catch this at this time and then start building our capabilities. And then while this costs come down, we should be ready to fully tap this technology. So today, more than 200 enterprises across the world are working on quantum. So when I say 200 enterprises, these are large enterprises. Many of them are customers of TCS base. So I removed the logos. So initially, I have logos of all the companies that were working here, but just to avoid some copyright issues and all those things, thought I removed this. Uh, also have some more examples that are available on public domain. So you can imagine these are some of the use cases that what they are working on. So just to give a flavor of things, uh, they're working with UK-based Cambridge Quantum Computing, so which is now called Quantinium. So they're working on drug discovery development for Alzheimer's disease. Coca-Cola, so they're working in Japan, so to work on this optimization of servicing agents to the 700 vending machines that were there across Japan. So the Japan network is 700 vending machines. They're trying to optimize this scheduling of the service personnel to these vending machines. It's Nestle, so it's an important and interesting use case. So they're trying to bring consistency in the food, like all of us must have tried these chocolates, Maggie, etc. All these are nice products coming from Nestle. So we expect this consistency of taste, aroma, and nutrition, and all those things, right? So and then they have modeled these problems into thermodynamic models. In fact, I'm very keen. I request some of you to please go and look into this use case, how they are doing it and what they are doing it, and then see if any of these things can be applied to Indian foods like idli and dosas. So wanted to understand that. So here they are trying to understand these thermodynamic models of how they are interacting with water molecules and with lipids, and then trying to bring this consistency in food taste, aroma, and nutrition. So this is the problem that they are working on. So Volkswagen, so they're working on optimizing taxi routes in Beijing. Verizon, so they're working on quantum key distribution. This is a security use case. We'll come to that in a little while. Enel, which is energy leader, so they're working on workforce scheduling kind of activities. So we can also use them in, so let's say telecom planning or telecom network planning. So these are complex use cases. So these are some sample use cases. I just want to give this confidence to you, saying that there are companies that are already working on it. So because for many people, they still think that quantum is only research. We don't know what we will get it, and all those that kind of mindset will be there. So, but just believe that all these are companies that are experimenting on quantum, and there are people who are working on quantum, and there are a lot of opportunities that will evolve as this technology develop, and then it might naturally fit into the conventional AI, classical AI, and remain on the sides of AI, accelerating AI. But it's important to understand the kind of problems that you can pick and then run on quantum machines, thereby creating enormous value. So we have plenty of problems in a country like India. So the public health distribution system is a complex problem. The railway scheduling system itself is a complex problem. The crew scheduling for a particular airport is a complex problem. So all these are complex problems, right? The loading and sequencing of railway containers on a railway zone is a complex problem, right? So if you try to identify the literature of all these problem statements that I mentioned, you will be surprised that you'll not be able to solve this problem for the bigger number of variables. So it was actually a huge surprise for many of us. One customer told, so we can solve only up to some X number of containers, and we want to go to 2X. So surprised to see that these are extremely complex problems and can create significant value when we try to attempt these problem statements. Right. So we're close to 4:30, but quickly run through the slides here. So again, we talked about this quantum power, talking about exponential and quadratic speedups. So now, so what if these people use the same quantum power to break these encryption schemes, which are also mathematical algorithms? So the RSA algorithm that we use, which is used in public key cryptography today, is based on a mathematical model. So RSA 2048 is a very common encryption scheme that we use. So which is a mathematical problem. So these things can be broken with quantum machines, and there are papers that are people publishing that this can be broken with some 3 million qubits. So the latest one that we have seen is people claim we can have, if you have good quality, 384 qubits. They've written a paper. We don't believe that. China has even published another news item which is very difficult to believe. So yeah, I think RSA is the name of people who built this algorithm. So this is a very popular public key cryptography algorithm, so which is based on prime factorization. So this is the algorithm we use in asymmetric cryptography. Uh, so the problem that we will be facing is what if stores all our data, like WhatsApp messages, we are storing it in our Google Drive or wherever, so which is based on certain encryption scheme. So what if somebody breaks this data after 5 years and then uses it to blackmail the people, right? So that kind of things are possible. So what we need to do? So there are some foundational algorithms that people have shown how this RSA algorithm can be broken. So they've shown it for small number of uh, bits. So the immediate question in front of us is how do we get protection? So luckily, so it is happening in the world. So the people who have actually created algorithms which are quantum safe. So NIST, which is a US based organizing a competition in 2015. So they invited people to submit algorithms which are quantum safe, and they screened these applications. And last year, in the month of August, they announced three schemes, and they recently announced the fourth scheme, and they also announced a lightweight scheme last month. Right, so we have different now new standards that are coming or that are announced by NIST as standards for cybersecurity encryption. Right. So this creates a new set of business opportunities. So where all our conventional encryption schemes, we need to migrate onto the new technologies, new encryption schemes, which are quantum safe. This classical mathematics. So, but you only need to shift your classical encryption algorithms onto new set of algorithms and test all your infrastructure, whether these things are not causing any experience mismatches, doing things well. And today you cannot prove also, but the hope is that even a quantum brings a 3 million qubit quantum machine, we can still feel that we are safe. So, but because these are again mathematics can be broken sometime. So we need ultimate security for that one. So we use something called QKD, so which is another technology that is evolving. So the big countries like or say let's say the governments in US, Germany, Singapore, they have given advisory saying that people have to migrate this into new and by 2030. India is still in the process of preparing these guidelines. So there are two, three task force that are actively working from IT, DOT, and DST. So are right now preparing the guidelines on how India should work towards future. So this is another interesting opportunity that is developing. So all people who are interested in cybersecurity and cryptography can look at this area. So and there are opportunities for migration into the new encryption schemes. That's a huge business opportunity, and we are working already with few customers on such opportunities. So there are examples of some of the banks that are working on quantum security. So you can see a lot of interesting logos in the US. So all these banks are already working on these migration strategies. In India, there is not even a single bank that is working on this, that are experimenting, right? So in India, it requires RBI to put this requirement in their cybersecurity framework. So RBI follows something called RBI Cybersecurity Framework, which is used as guideline by all the banks. So they create this guideline in cybersecurity framework, then all Indian banks will also do it. So get ready for this opportunity. So you will have interesting use cases coming from banks, their applications onto quantum safe encryption schemes. And it's a huge effort. Previously, it took about a decade for people to migrate from one encryption scheme to another encryption scheme. So it will take good amount of time this time. And now we are also giving one more flexibility of giving the choice of encryption algorithm to the end user. So previously, this you do not have much of the choice, but here in the new generation of cybersecurity standards, so people are putting these encryption schemes flexible so that customers can switch. Tomorrow, if a more powerful quantum machine comes, you have to switch to a new scheme, and it happens at an abstract level. So those are things that are happening in. So watch out this space. And the last technique is quantum. This is the ultimate security method. So we use quantum effects to generate these keys. So the switches will look something like this on the right. So this is a box from one of the startups from India. It's called QT Labs. They use a laser and photonics to generate these keys. And these keys, if you try to tap, so you will actually change the state, and the party who is monitoring this network will know that somebody is actually intruding the network. So this is a new way. So in India, CDOT and QT Labs and a few other startups that are working on this technology. Under National Quantum Mission Program, there's a goal to set up 2,000 kilometer such line, QKD line, uh, which is which is the ultimate security. So countries claim that they have their own internets. So this is actually building their own network, and and if somebody tries to intercepts or interrupt this network, you will know that there's some disturbance in the network, and you can switch the keys or change the switches or whatever, right? So this ultimate thing that is going to come in future, and people are doing this over satellites as well. So it's called satellite key distribution. So again, ISRO and QNU Labs, they're working on satellite QK, that they've transmitted these keys over satellites over long distances. So again, so these are topics still evolving. Here is to build switches like this, reduce the cost of the parts that goes into this one, like the lasers, the photon devices, photon detectors, cameras, etc. And how do we make this switch affordable? Today, this switch costs about 2 crores. Can we reduce, unless this switch comes to about 2 lakhs? We'll not use it, right? So the commercial viability is still some time away, but the cost of components is drastically coming down. So which means these technologies will be available. So if you look at a company called Sienna, so they have some nice switches that are used in transcontinental communications. So they started putting PQC and QKD into their switches. So 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 these things will become commercial sometime soon. Now imagine the network architectures like 5G. If you're working on 5G, so imagine it is a full 5G network. You have to transform that with PQC and QKD. So there are places where you need to get this security layers reimagined. So these are some of the problem statements that are open for research. So you can check or see the developments happening in that area. For example, you can search for quantum in 5G and quantum in 6G. 6G quantum is being adopted as one of the initiatives. 6G standard. So which means when we see 6G, you'll also see quantum encryption. So it's a lot of action here. And then so we have quantum sensing, the last topic. So here it's another interesting area. So just like computing, a lot of activity happening here, and these are actually considered to be near term compared to the computers. Our MRI machine is already a quantum machine. So here, if you use quantum sensors, you can actually transform the same MRI machine into another helmet like this, which can do the magnetic sensing. So you can also do electric field sensing. You can do time calculations with 10 power 9 minus 9. You can also measure the gravity measurements and acceleration and rotation of inertial sensing, all those things that uh, beyond the classical limits. So this is much more precision sensing, which means when you have good quality data, so you can use the same thing and apply classical AI, or you can also apply quantum AI and then get even better results. So you'll have quantum microscopes, so quantum magnetometers, quantum atomic clocks. So right now we use a cesium clock, which is our National Physics Laboratories gives time based on the cesium clock, but we'll shift to these atomic clocks in 1930. So the sorry 2030, when this will become a standard, right? So a lot of activity. Yes, we have some nice labs like ICER Pune, IIT Bombay, IIT Kanpur, IIT Madras. So these are places where a lot of research is happening around sensors. Uh, in the interest of time, not able to get into this one topic, but we are working with IIT Bombay for magnetic sensing, something like this, a sensor using NV center diamonds. It's called nitrogen vacancy center diamonds, and we're providing the software stack for this one. So the goal is to do better magnetic sensing devices or determine semiconductor imperfections and things like that. That kind of use cases, mostly healthcare use cases. So this is another area. So you can again see a lot of electronic of image processing, machine learning, and classical AI goes into it. So by this time, you must have understood some good amount of multidisciplinary subject and things that we already know can be applied here. So these are things. So this is an experimentation of quantum diamond microscope from IIT Bombay. So this is an example of a current system, but you can imagine this entire setup become a small chip and a small microscopic microscope machine. Right. So that is what we're getting into. So miniaturization of these kind of components, keeping the optics principles. So that is, and that's the reason why this is very, very multidisciplinary. We also need help from the healthcare professionals who can understand this. Uh, so the study of tissues and study of the human body, etc. So all those aspects are required to build technology around this one. So this is use cases. A few slides around National Quantum Mission, but I will maybe take this separately later. Available in public domain for you as well. So some of Indian startups who are working on quantum, so, and we have which is coming up. Okay, so I'll conclude with this slide. So typically, a lot of customers ask me, so what is so again they'll tell also following the technology, they will tell so tell me what is new in the last 1 year, right? And I go with this slide to them. So maybe 2026 is a year where we see some commercial advantage. So we are already seeing in some form uh, in classical quantum hybrid things where customers are liking the approaches, but still not commercial advantage. IBM says 2025, say let's be at the half of 2025 anyway. So let's say what is required. So we need machines. This machine should get into data centers. We also need better algorithms. Can we network these quantum machines and create more power? So though even you have say let's say 156 qubit machines may not act as 750 qubits, but still good power when you network them. And then the cost, which is coming down. So these are things that are moving variables right now. So when they get better, so we see an action point, and we're waiting for that ChatGPT kind of movement here. And what is required from the organizational perspective? So we have complex skill requirements, the choice of problem statements and selection of these algorithms is not easy. So significant cost implications that are there. Still, we are working on learning together, understanding this what community is doing, and then we also apply our knowledge and share the knowledge to different people. And that is exactly what we are doing in this FTP. For our customers, what kind of implications they have? So they have to redefine their R&D pipelines. They cannot imagine that without quantum machine in 2030, if they build a data center or they make an investment, it is not right. To understand their investment strategies, they have to manage the talent. Most of our customers suffer with not having people who understand quantum or who can't even talk quantum. So that's a significant gap. And today we support from TCS perspective. But when we are doing multiple such POCs, difficult, even we'll not have teams. Right? And then you have to get ready for the cybersecurity implications because there are already regulatory guidelines that are already there for them. By 2030, they have to switch in US, Singapore, and Germany. So there are opportunities here. So if they don't do that, there will be penalties and they cannot sell their products in the US geography, right? So that's the problem. So while this is happening, so we have two timelines here. So one is the number of qubits. Google and IBM has given a million qubit roadmap by 2029. IBM it is 2033. So this is maybe when they started, they also mentioned 2029, but later they adjusted the timeline to 2033, a million qubits. But if you look at the semiconductors, so here also a lot of interesting things are happening. Like our mobile processors are now at 3 nanometer, and we'll see at 1.4 nanometer by 2028, 2029, right? So which means here also the power is getting better, and we are getting some very new interesting architectures on the classical AI, so which will shift this inflection point a little bit probably. But nevertheless, some problem statements cannot be solved on classical machines irrespective of whatever power you have. So, so that's the reason why there's a very nice intersection between quantum and classical. So we will see this inflection point in some time, and that's when uh, we will see the benefits of quantum technologies. And it's important for all of us to learn together and then harness this technology. So with this, I'll conclude this session. So this is the stack representation that we talk. So TCS works only in these top layers. We leave rest of the things uh, for the ecosystem to work for making quantum machines, and to work on this zone and build new products for the country, and also open to on interesting problems in the application area. So this is the expectation. So, and the National Quantum Mission similar theme. So they want everything made in India and then build best of the solutions coming out of our efforts. And uh, and we should stay as leader in this technology area and lead from the front. So with that, I'll conclude this. So I do have some takeaways. So it addresses all branches of engineering, huge generating good number of jobs, a level playing field. So we are all of these big countries. So we have to start. Uh, maybe we may not have some hardware capabilities, but we can definitely this time learn this and move forward. And especially on the drug discovery side and optimization, we can solve problems because of software capabilities. Sensing, we have good capabilities coming up from different. On the security side, we have a huge opportunity. And then what we will really see is when we make this um, Indian IP in the area of carbon capture, battery materials, catalysts, etc. And and today there are no drugs for malaria and sickle cell diseases even till today, right? Dengue, we don't have a drug. And is it possible with quantum? So maybe that's an open question for all of us, and we should work towards these kind of problems. With that, thank you for this opportunity, and I hope I'm able to give you some knowledge and information. So please feel free to shoot the questions to me, and I'll take them offline and I'll respond to you um, through the Emmanuel sir and APSHC. And yeah, there's questions like machines. Yeah, this can be infected. So that is uh, because there is a classical interface to these machines. So it's possible. So all those things can, some of the questions that I will see and I'll respond. But feel free to contact me and shoot out the questions, send it to the team, and I will respond back with the answers. Can be hacked is a question. So these machines, so yeah, hack means taking the control or seizing the control. Yes, can actually. It can be dangerous more if you try to hack these kind of machines because already coming up with significant amount of capability. Technically, yes, it is possible to hack the system. Yeah, we also do some internships, so can send you. uh, So this is so right now not many, but overall I can tell you India, because of the National Quantum Mission, there are maybe about 500 plus openings as of now. People are looking for, you can see job profiles coming from different labs and things. So please feel free to uh, apply to these institutions or visit these institutions, not even apply, actually visit these institutions and learn more about quantum. And once we have this 156 qubit, please feel free to stop by. TCS team will be there to host you. So with that, and thank you so much for your patient listening. And I'll get back to you with the responses to the questions. I'll share the presentation as well. Yeah. Over to you, sir.
Thank you. Thank you so much, sir. Thank you for your wonderful insight and many things that you shared. Yeah, yeah. Thank you, sir. Thank you, Sridhar, sir, for being there and giving so much of data and information. And it's a big overview. That's what we can look at and just
All right, I'll look into the questions and then respond. If you can collect these questions and share it to me, I'll respond and get back to the members. We can generate this
sure,
as a
sure,
FAQ
sir.
and share it.
Yeah, I'll try to get the questions and then yeah, you can exit, sir. I think you have a
Yeah,
meeting,
yeah.
so we'll
Thank you,
take
sir.
it forward. I'll just respond. Right. Thank you so much. Thank you.
Thank you, everyone,
Thank you for
and
joining.
yeah, thank you, sir, and thank you, everyone, and best wishes to all of you. Bye.
Right. Yeah. Dear participants, if you have any questions, you continue to write it in the chat. We'll take it forward. And once sir has uh, exited, yes, if there are some questions which I can answer, I'll try to answer that. And otherwise, we'll take the questions back to sir. Yeah. ऊपर चले जाओ एक बार और ऊपर चले So do we have any? Okay. Yeah, Lavanya Bulus ma'am will try to answer the first question. Sir, do we have any hardware and software memory specifications for this quantum technologies? Yeah, as of now, the stack is not yet ready. The hardware is getting ready. As of now, most of the things are simulation. Some of the softwares that sir has mentioned, Qiskit, QIS, KIT, or Penny Lane, or Q Inverse or QSIM, most of them are simulation softwares and a little bit of quantum key distribution protocols and implementations, quantum optics, and some of these things are there as of now. Quantum processors are there, quantum processor time is there, but it's going to be difficult to access. So the full stack development as such, operating system, and then some more applications that can be developed on that will take some time. As of now, please try to focus on trying to understand the simulations and try to see, because quantum is not fully realized is what we can say. Yeah, it may take, as sir mentioned, that by January we will get the quantum access, and that quantum access will be less costly for us to access the system. That's one thing that we can do. But otherwise, as long as the computers don't become fully accessible for us, it will take a long time. So that is something. So as of now, we're just trying to understand how the things are happening, and that is what we can try to look at, right? So slowly the stack is coming up, and then we can build that, right? Internship qualification and fees, you can look up the website, TCS internship website, and then you can try to look at that, and then you can register. I think usually they start their registration process sometime in January and release their offers by April for the internship starting from May 15th or June 1st and going up till December. So sometimes it is few months, 2 months, or sometimes it is 6 months to 8 months, right? So that's the thing. Then you have how are the quantum dots utilized? Yeah, as of now, it is still in the nascent stage, but basically the material is what is to be discussed. So when we come to quantum materials, you understand quantum dots in detail. Of course, you can look up quantum dots on the internet or ChatGPT, and you'll get so much of information, right? In any possibility these machines are affected? Yeah, I think sir has answered this question. Yeah, that's there already. Will you please conduct hands-on workshop focus on problem solving? QT-03 is basic programming lab where we will try to introduce you to Qiskit. In fact, from QT-02 onwards, we try to give you some introduction to what are simulations, how they can be done and all that. Because basically what we're trying to do, please try to understand what classes you will teach to students is what we are equipping you, right? And what students can understand only. If you're looking at it from a research perspective, this is not the course where you will get all the information immediately, right? And those courses, as I mentioned, are not going to be available at 500 rupees. So they are like 80,000 rupees and all. You can contact QPIAI or Q Krishi or Q New Labs. Most of them have online courses, MOOC courses. You can study at your own and do that. They will start with simulation programming and all that, and then you can look at that. It will take some time before we do that. So please wait for some time, right? Any open access quantum simulators? Yes, you can look up Qiskit, IBM Qiskit gives you 10 minutes per day free, the quantum processing access. So you can write a code and run it. And 10 minutes is more than sufficient for the level of understanding that you have. But of course, if you are a researcher in quantum, it will take some time and you can pay money and IBM will be happy to give you the resources. It will be slightly costlier and then you will have to do that. And that's what when Sridhar sir is telling that Amravati, once we have the quantum valley set up and IBM quantum installed, there will be huge resource which government can give to researchers who can show that this is what we are able to do, and you will get sufficient time. Somebody will be there, a committee will be there who will sit there and try to analyze what you are doing and how much time can be given to you. So those things will happen from January 2026 onwards, and that's a great opening for us. But by that time, if you're able to come up with good solutions, catch up with some of the tools which IBM is giving, and you're able to run through, that will be a great resource that you can start. Open access quantum simulators, Qiskit, go to IBM Qiskit, just type IBM Qiskit on Google, you will get a lot of information. The tutorial, entire tutorial is there. You can do that, right? Anything else? What quantum algorithms are useful to detect cancer or other bio molecules? I don't think anybody can answer that question. You will have to read through. Please read cancer research. There are so many quantum papers on cancer research. Cancer analysis, image analysis, and data analysis can be done, and GPUs are not able to do that, and that limitation can be overcome by using quantum and quantum algorithms. So as of now, you will be able to run some simulated versions or real-time version, and you can see that recently one of my students worked on some quantum image algorithm problems, and he used the quantum 10 minutes time and could run some programs and show me something. That's what the best he could do. But when you start collect a cancer data set and try to analyze using existing GPU systems that you may have on Google Colab or something, if you're not able to do that, then you need quantum power. If you're able to do that already, then why do you need quantum is a big question, right? Quantum is needed for problems which cannot be solved by what is the thing that are there, right? Quantum computer is mostly good for solving special problems. Exactly. GPU also will not solve all problems. So GPU will run along with the CPU. So that's something which you need to understand, that CPUs are not replaced by GPUs. GPUs or CPUs will not be replaced by QPUs. Please understand that, right? So it's optimal to prescribe this as a common course for all students at the UG level. Yeah, that's the desire and passion of our chief minister. So that's the idea that we're trying to look at, and we are trying to put in efforts to do that for all branches of UG degree is what, because people will use quantum is what he's thinking. A few years later, that's going to be a reality, like how everybody is using AI, how everybody is using a mobile or what do you say, a laptop, or everybody is using. So we never thought that a computer will be used by everybody some few years ago, but now this is the time where everybody is having a mobile phone. I was talking to first year students and telling them, you don't have to buy a laptop in the first year, because if you want to run C programs or Python programs, you can run it on a simple browser which runs on your mobile phone. You don't need a laptop. If you have a mobile phone, Android based or iPhone, you can run programs on the mobile phone itself. So they are not being replaced. Please try to understand that. So quantum will address only specific problems. Obviously, cancer research is one of them. India has National Cancer Grid, NCG, but the data is not as of now available. But then to handle that huge data, then quantum algorithms will be needed. So please start with some small data sets which are publicly available, and then you can do that. Quiz 1, sir, not appearing on Canvas. Yes, it's not appearing because some of the participants are taking a second attempt. They are taking a second attempt, as I mentioned. They are taking a second attempt because they scored less than 4 marks. They started the exam, the power got off, so their system got shut down. So that 30 minutes is over, or their internet got disconnected, and by the time they used alternate methods to connect back, 30 minutes is over. Or maybe they suddenly were started the exam, but they were trying to refer to some notes to answer the questions. 30 minutes is over, so they scored less than 0 marks or score less than 4 marks. For them, about 10 or 12 of them, we have allowed them to take the second exam. So while they are writing the exam, the quiz is not visible for you. The quiz marks are not visible for you because it is only visible for them. So tomorrow afternoon or tomorrow evening, I think we are closing that. So you will be able to access that exam like that, right? So that's the